In this question, we're given this W and it's a set of all vectors W whose inner product with some fixed V is equal to 0. And we want to show that this subset of V, the vector space, is actually a vector subspace. So we're going to go back to our 3 axioms that we must do for this to show something's a subspace. We need to show 0 is in W. If W is in W, then any scalar multiple of W is also in the space. And if W1 and W2 are in W, then their sum is also in there. So we have to show, basically all 3 of these things. So I can start with the 0 vector one. So basically we just need to show that 0 satisfies this property of being in the space W. So we need to show that when I do the inner product with V, I get 0. Now, this seems like it should kind of obviously be true, but it's not actually one of the axioms that we have of these inner products. But we can make it so by just doing like a little bit of a trick here. If I want to calculate V with the 0 vector, well, the 0 vector is 0 times literally anything. So just for the sake of convenience, I can say it's 0 times V. Right? So those are true. Those are things that we know. Those are part of the, going way back to the axioms of vector spaces or subspaces. And now I can use the constant multiplier to pull the 0 out and say it's V with itself. And now it doesn't really matter what that inner product is because it's 0 times something. And that's going to be 0. So it's a little bit of a trick, but it does work for us. And it's just kind of how we would always show that the inner product of anything with 0 is always 0, because that wasn't given to us, but we have that now. And that implies that, yes, 0 is going to be in the space W. So that one's good. So now what we're going to do is, do the next one, show that W implies CW. So suppose W is in W. And so what that means, by definition of being in that space, it does mean that V along with W, so that inner product is equal to 0, right? That's the definition. So our goal is to show that any scalar multiple of W is also in there. So it also satisfies this inner product equation. Then V with CW, just like what we did before, I can pull that C out and get V dotted with W. And I know that that's 0 because, right, we just showed that that thing is 0. That was the requirement that we needed for W to be in that set. And so that is also 0. And by definition, CW is in W, right? That's what it means to be in W. It has this inner product. And then finally, the closed under addition. So I'm going to suppose that W1 and W2 are in W. And again, by definition, that means that I have these 2 inner product calculations. So V dotted with W1 and V dotted with W2 are both 0. And so I need to show that their sum is in the space W, which means that V, not dotted with, but the inner product of V with W1 plus W2 is also going to be 0, but it's just going to use these nice properties we have of inner products. Then V with W1 plus W2. Now we are allowed to tear that apart because, it behaves just like a dot product. It behaves very linearly. So I'm actually able to split this up. And we just showed that those two things are 0. So we do get 0, and that means that W1 plus W2, right, because it has this inner product with B to give me 0, it means by definition that they're in W, and therefore W is a subspace of B. And that's it.